In this tutorial, you learn how to set up the magnetic field module and frequency study, create and mesh the geometry of a rectangular conductor surrounded by air, apply coil conditions to simulate current flow, define user-controlled mesh properties, and calculate AC resistance and inductance of conductors. Let's begin. Hi everybody, in this video I want to speak about how to account for proximity and skin effect in a COMSOL model. Think of this question: how should I consider skin and proximity effect in a model? The short answer is using the magnetic field module. If you use the magnetic field module, automatically COMSOL accounts for the proximity and skin effect. However, I want to build a simple model in this video so you can explore more these two phenomena. What is proximity and skin effect? It needs an extra video to explain these two effects, but to put it very simply, the skin effect causes the current in a conductor to flow mostly from the outer area of that conductor. In other words, the current repels itself and flows mostly near the surface of the conductor. The proximity effect is quite similar when the current flows through two bus bars or two conductors which are near each other. The current tends to flow from the outer surface, and the inner surface of the conductors which are near to each other has a less current density. First, I simulate a very simple rectangular conductor to see the skin effect, and then I add another conductor near it to see the proximity effect. Okay, let's start. Open the model wizard, select the 2D, and here in the AC/DC module you can find the magnetic field. Open it, and there is an option that says MF magnetic field. Please add it to your model and go to study, and I want to study the frequency domain. Please notice that the skin and proximity effect only happens when you have an AC current, an alternating current, and in the DC this current does not happen. Therefore, we should consider studying in the frequency domain. Okay, I select the frequency domain and click on done, and we are ready to do our model. Because you are familiar with the geometry, and if you are not, please refer to my previous videos, I stop talking and just build my simple model. Okay, the inner rectangle is my conductor, my bus bar, and the outer area is the surrounding air around this conductor. I assign the copper to my conductor and air to my material. Let's do it. The material assignment is now finished. Here we have a copper conductor and it surrounds with an air domain. Okay, let's speak about our physics. In the magnetic field physics, we do not have the option of terminal. Therefore, if we want to inject current through a conductor or whatever, it's better to use the boundary condition or domain condition coil. Because my conductor is a domain, I select the coil from this part, which is the domain condition. Okay, I select my conductor as my coil. The material type should be solid because it is a metal. I do not change the coil name. I also let the coil group to be unchecked. And here, because we have only a single conductor, I let it be single conductor, but there are also other options like homogenized multi-turn, which I cover in my next videos. Okay, I want to feed 1 ampere to this bus bar or conductor. Therefore, I set the coil excitation to current and put it as 1 ampere. The rest of options do not need any change. The conductivity and also permeability and also relative permittivity are gathered from materials in the material section. Ampere's law, which is the base of the magnetic field, is solved in other domains, and you can also see the equations here, which are part of the Maxwell equations. Okay, everything is set, nothing else is changed. This is the magnetic insulation. What does it mean, the magnetic insulation? It means that the field cannot penetrate through these walls. In other words, the magnetic field lines forms only inside these walls and the field cannot penetrate through these walls. The initial value does not any change, and let's go to meshing. Because the proximity and skin effect deals with very small distances, the meshing should be at the smallest size. I set it to extremely fine, but later I show you that maybe this extremely fine option is not suitable for such a model and change it to a user-defined mesh. Okay, in this study I set the frequency to 50 Hz and everything is ready to compute our model. Okay, after the solution, you can see here the magnetic flux density. If I zoom in, you can see that the magnetic field inside the conductor is less than the magnetic field in the outer area, and this is shown that the skin effect works here. As an extra point, if you want to plot a variable only in one domain or a few domains, you can just come here. There is an option here which is called selection. Instead of entire geometry, you can set a domain and you can manually select, for example, your conductor. And if you plot it again, you see the variable only in that domain. And you can see that the amount of magnetic flux density is higher at the outer area of this conductor. Okay, let's come here to data set and define a cut line. I set it the x to -1 and the y at 0 and the 0.21 and 0. It is a line in here, and we are going to plot the current density over this line. Okay, I come here to results, add a one-day plot group and add a line graph. Here I select the cut line 2D and I come here under the magnetic fields. Here you can see the currents and charge, and this is the current density norm. If you plot it, you can see something like this. And the reason of this, especially from this side to this side, is due to the bad meshing. If you come here in the conductor, this is the conductor domain, you can see that from this part to this part you have 1, 2, 3, 4, 5 meshes, and because it is 2 centimeter, it equals, each mesh equals 4 millimeter. It is very large for simulating the skin effect and proximity effect. Therefore, we need a user-controlled mesh instead of physics-controlled mesh. Okay, I come here and change it to user-controlled mesh. And you see two things here. The first one is size, and you can just set the maximum size of the meshes here. 0.5 centimeter is very large. I set it to 0.2, and the minimum element size is also very small. I set it to 1.1 centimeter or 1 millimeter. Maybe set it to 0.5, and the maximum element growth rate I set it to 5, because here in this domain the meshes should be very small, but in air domain, the meshes can be very, very large. I let the curvature factor to be here. The free triangle sets these triangles in different domains because the mesh size in the conductor should be very small. If you use only one free triangle option for whole domain, the number of mesh becomes extremely large. And this is not the thing that we want because it needs a very large processing power to reach the solution. For that point, I right click on mesh and add another free triangle, and here in the geometry entire level, I set it to domain and select the air domain. Therefore, this is the option for, I can also set it to domain and remove this one. This triangular option applies to the conductor area, and this is to the air area. And because I don't want to add another size or define another size, I come here to scale geometry and set the scale geometry to 0.1. This means that the mesh size in the air domain can be 10 times larger. Okay, let's build all. You can see that the meshes in the air are much larger, but the mesh in the conductor domain is much smaller. I recompute my model and come here to my line plot. You can see a much further distribution of the current. You can also make your 2D cut line a little bit smaller. For example, because -1, I put it to -99 and here to 0.99. And if I come here, you can see a very fine distribution of the current across the conductor width, and you can see that the inner area, the current density is lower compared to the outer area. Okay, in the next task, I want to calculate the resistance of this busbar. If you come here in the magnetic fields, you can see that the out of plane thickness of this conductor is 1 meter. Therefore, what we calculate is the resistance of 1 meter of this particular conductor. For that, you need only come here to the right values, right click. You have a global evaluation. Just click here and replace expression under the magnetic fields. You can find something which is called coil parameters, and these are numerous number of parameters. For example, coil current, coil inductance, coil power, and you can also find here something coil resistance, and it is called the AC resistance, which says that the skin and proximity effects are included. I select that and evaluate this. You can see that 1 meter of this conductor at 50 Hertz shows 1.2 to the power -5 ohm. If we want to see this skin effects works perfect or not, I just come here under the frequency domain and set it, for example, to 250 Hertz, recompute that. We expect from this skin effect that the resistance of the conductor becomes higher with the frequencies higher. Okay, you can see here, if you compare it to the previous curve in your mind, the amount of current density here is lower. In the previous curve was about 300 ampere per meter, and here the amount of current is higher. But if I come here under the global evaluation and reevaluate this number, you can see that the amount of new resistance equals 2.4, and this is quite 2 times the previous resistance. Therefore, the skin effects works very good. You can also, as an extra point, calculate the overall amount of current that flows through this conductor. For this, I'll come here. We should integrate the current density over the surface of this conductor to reach the overall value of the current. I come here under the integration. I want to calculate the surface integration. Under selection, I select my conductor. What parameter I want to integrate? I come here under the magnetic fields, currents and charge, and I want to integrate the current density in the Z component, which is inward or outward. If I evaluate this, you can see that the amount of current equals 1 ampere, and don't forget in the coil parameter I set the overall current to 1 ampere. Okay, let's put two changes in our model. I add an extra conductor near this conductor first, and then I study my model for various frequencies. Therefore, I want to do a frequency sweep to see what happens when the frequency goes higher. Okay, let's add the second rectangle. Don't forget to check that the copper is assigned to both conductors, and this is the air. Very good. In the magnetic fields, this should also be selected as coil. Therefore, I select this one as the coil. As another extra point, if the selection bothers you, you can do two things. First, you can using the select box options. If you select this option, you will draw a rectangle. Whatever falls within that rectangle are selected. Okay, let's use this option, and the second domain is selected. You can also use this one to deselect some specific domains. And also another option is using the click and hide. The outer boundary, which is air, bothers me and does not let me to select the second conductor in this scale. Therefore, I click on this and hide my air boundary, and now very simply I can select the second domain as the coil, and when I finish I just click on this, which is reset hiding, and all my model comes back. Okay, this is the coil, this is the Ampere's law, everything is okay. But here I also want to add or apply my triangular option 1 to the second conductor as well. I use the select box option, everything is okay. This is the free triangular 1, free triangular 2, and I build the selection. Very good. The meshes inside the conductors are very small, and the air domain is very large. Now I come here to study, and I set my sweep to logarithmic. I start at, for example, 50 Hertz and stop at 10 kilohertz, and 5 steps per decade is okay. I select replace and compute my model. Because the selection is only on domain 2, you cannot see the magnetic fields here. I return it to the entire geometry. These are the magnetic fields. I can also duplicate this option to see the current density over the surface of my conductors. I delete these options, over this one, and I come here in the reflex expression, and this is my previous selected parameter, the current density, the Z component. I select a new plot. You can see that the amount of current is higher at the outer surface, and the inner surface, where the conductors are near each other, is much lower. Also come here to the cut line 2D and put the second part to 4.99. This is my selection that crosses the two conductors, and come here and you can see the plot for all frequencies. Just can come here and select the first frequency, which is 50 Hertz, and you can see that the amount of current is higher here, and lower when the conductors are near each other. And if you go through the last frequency, which is the higher frequency, you can see a much higher uneven distribution of the current over the conductors. Okay, I want to plot the resistance of these two conductors versus frequency. I come here and select one the plot group and select the global. The x-axis is automatically assigned to the frequency in hertz, and here I select the under the magnetic field. This is also here you can select from this the coil resistance. And you can see here as the frequency goes higher, the resistance also becomes larger, which is the thing that we expect from proximity and skin effect. It is also very interesting that you can at this point also calculate the inductance of this coil. I set it inductance, I set it to, for example, microhenry, and you can see the amount of inductance of these two parallel conductors versus frequency. It starts from, maybe set it to nanohenry. This starts for 372 nanohenry and falls to 352 nanohenry in higher frequencies. If you study and search the internet for the inductance change versus frequency, you can see curves just like this. As our final point, let's calculate the surface integration of our two conductors. If I evaluate that, you can see that the amount of current is still 1 ampere. Let's clear all of it and evaluate. You can see that on all frequencies, the amount of current that passes through both conductors together is 1 ampere. If you come here and in the coil option, set it to coil group, 1 ampere feeds through each conductor separately. Therefore, two conductors together carry 2 amperes of current. Let's do this. I changed nothing, just pick the coil group and recalculate my model. Then come our surface integration and evaluate again. There you go. Therefore, the difference between selection of the coil group or not, when you deselect the coil group, the current amount that you define here passes through all conductors together. If you select coil group, the amount of current defined here flows through each conductor. Okay, that's enough for this video. In this video, we have covered how to account for proximity and skin effect using the magnetic field module of the COMSOL multiphysics. In my next video, I want to explain how to calculate the mutual and self-inductance of coils and also conductors. Don't forget to subscribe now to the channel if you want more tutorials that make COMSOL easier to understand. Take care and see you in my next video.